Every day, yeah. No one is going and getting free food somewhere, right? Okay, you'll know how to start, right? Tweet. तुमने photo लिया कि नहीं? Find Wilfred's session. 1, 2.
Okay, so hi folks, I'm Wilfred and I'll be talking over dissecting the Go's garbage collector. So we'll take a deep dive into how garbage collection works in Golang. So you can check out my profile on my website wilfredalmeida.com. More on that later. So before we go into garbage collection, let's first understand memory allocation, and should you at all as developers care about memory. So when you, let's just take this simple snippet. I hope it's visible till the end. Can you read it? Okay, so it's just a simple pseudocode. You have a variable, you declare it, you assign it a value 10, and you use the variable somewhere. So your work with the variable is done, and there is some data that you put in the memory. So
कैमरा बंद कैमरा बंद नजर
So you use the data, and what happens then? Because the memory that you allocated, the memory is still occupied and resources are limited. So the answer to should you care as developers, yes, you should absolutely care about the memory that your program uses. So before understanding let's understand the need of the garbage collector before going into garbage collection. So let's take a very practical use case. You are making an e-commerce application. So on e-commerce application, users place orders. So and you have to persist your orders in the database. So when a user places an order, your backend system will process the order and to store the data in the database. So your programming language will create an object and it will store it in the database. But after the work of saving the object in the database is done, what happens with the object? It stays like that in the memory. So you need to free up the memory. So in languages like C, you have to allocate the memory, you have to ask for the memory, and then you have to return the memory. But as programmers, suppose you have a client who says that I need a website up and running in 7 days, and you're charging your client for that. But most of the time is going on figuring out where your memory leaks are happening. You're spending your efforts and time taking up memory, freeing up memory. So that is sort of wastage of efforts. So that's why if the process of freeing up memory could be automated, if there is an automated and better solution. Because as humans, we definitely make mistakes while freeing up memory. So considering that problem, garbage collection is important. So to solve the problem of your garbage collection, the garbage collector is introduced in various programming language. So Golang also has a garbage collector. So focus on this statement. Go's garbage collector is a non-generational, concurrent, tricolor, mark and sweep garbage collector. Lot of jargon. Again, Go's garbage collector is a non-generational, concurrent, tricolor, mark and sweep garbage collector. So yeah, I am seeing similar sort of expressions here. So we'll take a look at each and every term now. So before beginning, let's first understand a scenario in garbage collection, that is stop the world. So stop the world, what essentially it means is every executing Go routine is stopped. The application is paused. So your application does some processing. The processor is assigned some tasks to perform. So all those tasks will be halted. Your application will basically pause. It won't do any processing. Suppose it's an e-commerce application, a user tries to place an order, that order won't be processed, the Go routines are stopped, everything is at a halt. So this is stop the world because the application stops. So that's the stop the world scenario. So after let's see the phases of the garbage collection. So there is the mark and sweep algorithm. So the mark and sweep algorithm, there are stages in that. So the phases of garbage collector are you need to mark the objects that are to be freed in the memory. So before marking, you need to stop the Go routines from accessing the memory, because what happens is mark setup is stop the world. The stop the world, why? Because I am trying to free up some memory and the thread is trying to write to that same memory. So that shouldn't happen because some critical data is written and the memory is freed. So that shouldn't happen. So that sort of arrangement is done. Then the memory which is to be freed is marked, and then after the marking is done, the memory will be cleaned and then the mark termination. So basically we stop the word, now we'll resume the program. So the program is resumed. So one quick note is that all these steps seem like they might take some time, but these things happen in fractions of seconds. Like nano and microseconds time is required for these things. So yeah, this is the timeline, the same thing, mark setup, marking, mark termination, and then the go routines will resume. So first phase is mark setup. So when garbage collection is initiated, a write barrier is is turned on for the go routine. So basically the go routines cannot access memory. New memory cannot be allocated. Any updations that have to be done in the memory cannot be done. A write barrier. The go routines cannot write to the memory, so it is a write barrier. So that is stop the word basically, because the go routines, if the routines cannot access the memory, then they cannot perform any task. So they are stopped. Then let's suppose that these are the 4 application processes that are running. So these are processing let's say go routines. These are processing the application work, 4 of them. So all 4 need to be stopped. So unless if 3 are stopped, 1 is still running. So the garbage collection has to wait. Everything has to wait until the 4th process stops. And let's assume that the 4th process is running some sort of critical operation, like it's traversing a list. A simple for loop is going on, but let's take the example of an e-commerce. And e-commerce, suppose you are calculating the sum of price, whatever the user has placed the order, you're just trying to sum the price up. So for that you have a list of products and you are iterating over the list. So while this suppose it has like 1,000 objects, the list has 1,000 objects, and you cannot stop in between, like 200, 500 are processed, and then you cannot stop this sort of code. Once this whole thing completes, only then you can stop it. So for that there might be in some cases an additional waiting time. So moving on. So after the all 4 routines are stopped, the write barrier is erected. Now the world is stopped, then the marking phase begins. So the phases, the steps in marking are: find root pointers from the heap to the heap from the stack. So we'll take a look over that. So basically 2 types of memories are maintained, stack and a heap. So then traverse the heap graph. So garbage collection works in heap. Stack is last in first out order. So stack is not concerned with garbage collection. Garbage collection happens in the heap. Whatever dynamic locate, you make an object, the object will be stored inside the heap. So and then mark heap values that are still in use. Once you go to the heap, look that which all values are being used. Once you find out, okay, these values are being used, so these have references from the stack. Okay, so these are the values to be kept, and the values that don't have any pointers to them, those are garbage, and clean them up. So that's how memory will be free. So here we'll take a look at these 3 steps. So the first step here is find root pointers to heap from stack. So here this is your stack memory. So stack memory has, let's say you have a function that you have written, then the stack will have the code of the function, the exact code, and then it will have pointers. So suppose you made a struct, you made an object from a type definition. So that pointer, that object will be stored in the heap and its pointer is here. So these pointers in the stack are called root pointers. So first find the root pointers in the stack. Then the second step is traverse the heap graph. So traverse the heap graph. So while traversing, what happens is go to the first node that is being pointed, and then from there it's basically graph data structure. If you are aware of graph data structure, it has edges. So just do a simple graph traversal and go to every node that you can and mark that, okay, I visited this node. So if suppose I am considering this node, so whether or not this node is reachable. So a go routine suppose wants to access some memory, it will go to this stack. From that stack it will go here, then it will go here, and then it will go here. So there is a path to this node. So this memory is in need. So it is marked. So similarly, whatever memory has, whatever the graphs have a pointer, those are marked. And this memory, this is stale because these edges don't have any pointer to them. So this is the memory that is to be cleaned. So when the garbage collection happens, when the memory will be physically freed, these 2 are the ones in the heap that would be removed. So yeah, so I hope the idea of marking was clear. So marking is a concurrent and the collector takes 25% of available CPU capacity for itself. So we have four, so our program was allocated four processes, computational processes. So 25% of whatever processes that are available will be used for marking. Because the operation of marking, you need to go here, you need to go here. So this also requires compute. So a process needs to work on that. CPU is physically required for this thing. So whatever the available resources are, 25% of that. So we have suppose 4 here. So one of the thread, one of these go routine, initially it was processing application work just like everyone else, but now it will perform the work of the garbage collector. And what is the work? It has to traverse, it has to go to the stack, and then it has to go to the heap, and then it has to traverse everything. So yeah, then there is the phase of mark termination. So basically marking is done now. Whatever memory is in use and whatever memory needs to be freed, that the garbage collector knows that. So the marking marking stage is done. Then we have the mark termination. So basically, the half of the work of the collector is done. Now the application go routines, the actual processing of the application can be resumed. So various cleanup tasks are performed, and next collection goal is calculated. So it will try to figure out that okay, I did a collection now. So when should I probably do the next collection? When should the next garbage collection run be initiated? It will try to figure that out, and then finally the write barrier is turned off. So the write barrier was that no go routine was allowed access to memory. So the application was paused. So basically the application is now resumed. So after the write barrier is turned on, the application, the state of the application would be something like this. So all of the available process threads here would be again go back to processing the work of the application. So suppose if your e-commerce application, a user has placed an order, then the order will be now processed. So sweeping, then you might be in doubt that okay, the memory was marked, but I didn't say anything about the memory being physically clean, because these two nodes that are to be removed are still in the memory. So when does that memory get freed? So that sweeping happens when a go routine asks for new memory. So sweeping happens when new allocation is to be done. It's not the part of the garbage collection run. The garbage collection run will only figure out what I need to clean. The actual cleaning will happen when someone new wants to take the memory. So a new go routine asks for a memory, then the allocator will go, it will free the memory, it will clear, and then it will store the new data there. So this thing also has latency, it requires time. So the latency of sweeping is not added in the cost of garbage collection, the allocation. So if you do frequent allocations, then it has to first clean the memory and then it will try to allocate the memory. So the latency is not in the garbage collection run, it is in the allocation run. So this is an important point to keep in mind. And again, when to run garbage collection, because the idea of garbage collection, I hope that it's clear. But when to run it, when to garbage collect. So determined by GC percentage, garbage collection percentage. So just pay attention to this second point. Garbage collection percentage ratio representing how much memory can be allocated before starting the next collection. So again, ratio representing how much memory can be allocated before I can do the next run. So this environment variable will come to it. So suppose the current memory usage of your program is 4 MB and the garbage collection ratio is default is 100. So suppose 4 MB is used and 100% of when more 100% of current memory usage, more 100% of current memory usage is allocated to a garbage run. So when 8 MB of memory, so 100% of 4 is 4. So when more 4 MB, so there is 4 and more 4 MB of memory is allocated, total 8 is there, then it is examined with the garbage GC percentage and then it will trigger a garbage run. So this garbage collection percentage can be set by the GOGC environment variable, GOGC environment variable. So if you set it to let's say 50%, so whatever the current memory usage is, 50% of that. So if 4 MB is the initial usage, when 2 more MB of memory is allocated, so total memory usage goes to 6 MB, a garbage collection run will be triggered. So depending on how your code is, because as developers, if you know that okay, I'm not assigning memory frequently, so why do I need garbage collection runs to happen? So you can actually increase the percentage to let's say 200. So unless there is extensive memory allocation, the garbage collection run won't be triggered. So this flexibility is a good thing that is in garbage collection. But garbage collection also has a problem. So let's quickly go over the case study of Discord and why Discord had to move one of their service from Go to Rust. They rewrote their one entire service. So there is a read states service. It simply keeps track of what channels and messages you have read. So if you use Discord, you know that it needs to keep track of what you have read and what you have not read. So for that they have and this services exist every time you connect to Discord, and Discord has users in millions, and every time these millions of users connect to the Discord service multiple times a day, so you just think the type of traffic this handles. The requests are in millions every minutes. So what the architecture of the read state service is, there is your Discord client running in a web browser. Then this is this LRU cache and the Cassandra database. So this LRU cache is written in Golang. So what LRU cache is, least recently used. So I'll keep data in my cache, and whatever is least used, I'll remove that. So whenever I need to put in more data in the cache, I'll check that okay, what is the least used thing, and whatever is the least used data, I'll flush that data out. So that is least recent used cache, and it was written in Golang. So what their team observed is there was this problematic CPU spikes. So if you can see these graphs, this is the system, the CPU usage. So you can see there are these spikes. The runs, then there is suddenly a spike. Then again the run happens, then suddenly a spike. So these spikes were being encountered, and they couldn't figure out that every 2 minutes why are these spikes happening. So these spikes also increased their response time, because whenever CPU usage was high, there was some underneath work going on, and these spikes were not because of the application slow. They were because of Go's garbage collector. So if the garbage collector is occupying CPU, then it obviously cannot perform the work of the application. So the response time that exists increases. So because CPU was not available for them. So understanding these spikes, so this is directly taken from the blog. So instead of freeing memory immediately, the memory that is out of use, memory hangs out for a bit until the garbage collector can determine if it's truly out of use. During garbage collection, Go has to do a lot of work to determine what memory is free and which can slow the program. Because the heap memory, it traverses the whole heap, so it has to figure out what memory should I free and what memory should I keep. So the traversal that happens, that was the time consuming job. So the code, and they knew the code they had written, it was very efficient code. They knew that we aren't doing allocations. So there shouldn't be logically any garbage cleaning work that Go has to do. Then why are these spikes? So Go enforces a garbage collection run every 2 minutes. So no, even if memory is not allocated, Go is designed such that every 2 minutes by default a garbage collection is triggered. So the spikes were every 2 minutes. These spikes are every 2 minutes. So because an automated garbage collection run happens, so regardless of heap growth, Go will still a garbage collection is happening. So whatever the steps are there in garbage collection are still happening. So the CPU was being used by garbage collector rather than the application. So the main culprit of the spikes, again this is an interesting thing, spikes were huge not because of massive amount of memory was ready to free, because they wrote in the blog, they had designed the service such that there wasn't any more memory wasn't allocated, but still why is the CPU usage? So the garbage collector needed to scan the entire LRU cache in order to determine if the memory was truly free for references. Because as we saw earlier in this step, it has to scan this whole heap. So whatever the entire LRU cache, whatever the entire services, whatever the entire data is in the memory, it had to scan this entire data. So even if the data is in use or it is not in use, it needed to be scanned. So this scanning time was actually the main problem that was, so that they didn't have, because as developers they know that okay, if I'm allocating 4 objects and these 4 objects will stay in the memory for a long time, I'm not explicitly freeing them, then why is the garbage collector looking whether or not to free that memory? So the main culprit was that it had to scan the entire LRU cache. So the shrinking the cache size resulted in frequent database hits. So what you can do is it has to scan a big cache, so reduce the size of the cache. It has small cache to scan. But the architecture is this LRU cache is synced with a Cassandra database. So if the cache is small, obviously there will be a cache miss. Data won't, because the cache is small, so there isn't the data isn't present. So then you have to hit the database. So even if you have a explicitly built cache, the load on that database was increasing. So the point of this cache, having this cache service, was not as per their standards, because the database load was still heavy, and doing operations from database takes time. And when you load Discord, the users need to, the response time really needs to be in microseconds and nanoseconds here. So they cannot afford a database hit. That's why they build the cache. And again, if the cache is causing an hit to database, then it's pointless basically to have a cache. So the cache size resulted in frequent database hits, so they couldn't keep this thing also. So the solution was Rust. They had to migrate this service to Rust. So Sahil has a talk in Rust, so he'll go over how Rust handles this problem. But I'm just giving a brief overview that Rust doesn't have a garbage collector. So if garbage collector, just think for yourself, if there isn't a garbage collector, how is memory freed? Because this is a question. So when I first encountered that Rust doesn't have a garbage collector, I was like, then is the programmer responsible? So no, the programmer isn't responsible. The memory is handled automatically. But then who frees the memory? Because that is the main question. So Rust uses a unique concept known as ownership. So it knows which object or which function owns which memory. So suppose you have a function that creates 3 objects. So it knows that function A created these 3 objects. So when the use of this function A is done, obviously this memory, the function made the objects. So now the function's work is done. Obviously the memory's use will be done. If this memory needs to be preserved, then the programmer will explicitly state that after this function call is done, I would like for this memory, the 3 objects that are created, to be preserved. So keep those 3. So as developers, you have to explicitly specify that. There is no need for the garbage collector to come and look. Even if the function is done running, there doesn't have to be any additional entity that has to come and see that, okay, do I need to free, that sort of thing doesn't happen. So it knows immediately when to free the memory, basically, because once the function is done, also the job of the memory it asked for is done, so remove it. So when they implemented their service, these were their results. So if you can see, the purple one is, so the straight line you are seeing, Go is purple. So the spikes you are seeing is Go, and then the straight line you are seeing is Rust. So because of the absence of garbage collector, the spikes weren't happening. So this is what they achieved performance metrics. And they also mentioned in the blog that the service, when they optimized and improved their Rust service, it was able to beat Go in every metric. They didn't specify which metrics they used, but whatever metrics they used for their specific use case, Rust was a better choice. So this is a keyword for, it has a link for Discord's official blog. In case you want to read, you can just scan this keyword. So we'll just wait while you scan. Okay, so moving on. So this poses a question that is Go inefficient then, because there were CPU spikes. So if you, as developers, you might be wondering, if I write a service, then would there be frequent CPU spikes and would it be inefficient in my program? So the answer is no, Go is reliable. It depends on your use case, because what Discord's use case is, they specifically knew that they weren't allocating any new memory. So they didn't have the need for Go's garbage collector, because they specifically knew. But suppose if you are building a platform like Google Cloud, where you are provisioning virtual machines, so you don't know which virtual machine has asked for which piece of memory and stuff like that. So you need something automated to take care of the memory there. So it depends on your use case. So when you're trying to just figure out which language to use or which technology to use, rather than ease of development, these parameters are the one you should be looked at. So we often ignore the cases of software engineering. So the UML diagrams, the class diagrams. So these diagrams are often ignored as beginner developers. But once you draw those, when you draw a class diagram, you have the whole architecture of your application in your mind. So then you can figure out, you can get a rough idea that whether or not my application will spawn multiple objects. And Discord's use cases, their cache was needed to be performant. They needed the performance. but you have to ask the question that just for a really small fraction of CPU usage, do I have the flexibility to go there? Because Rust comes with its own complexities. So whether or not when you're choosing a technology, you should dive deep into these things and try to figure out which is best suited for your use case. So, and that's all. That was my talk on Go. So, if you want to check out my portfolio, you can scan this QR. It leads to my portfolio website. We can connect later on. And yeah, that's all. Thank you. Thank you for staying awake. So, any questions? Yeah.
So you said that, and Discord said that they had to switch to Rust because of the garbage collector spike. But Go has an option to disable the garbage collector. And if you want to free memory, you can implement your own garbage collection as well. Then what's the point of switching to another language for the small case?
That's Discord's decision. So if you give the blog a read, you will figure out that they mentioned that they tried various optimizations. It was not just shrinking the cache size. They tried various optimizations and then they discovered Rust. So initially they figured out, let's just build a test product in Rust and let's see what the performance is. They tried out a new thing and they figured out that okay, this new thing, because we aren't allocating much objects, so we don't need frequent garbage collection. And Rust doesn't have a garbage collector. And we have a minimum viable product to show to our management that okay, the CPU usage is less here. So then they gradually migrated. So it was not that decision that okay, we need definitely Rust. They tried out Rust. Once they figured out okay, for our specific use case, Rust has a better performance, then they migrated. So now the service is completely migrated. I do recommend giving the blog a read.
Actually, I had read that,
Okay.
though I don't remember. But that time I didn't know that Go has an option to disable the garbage collector.
It depends on your use case because Go is structured, Go is designed in such a way that garbage collection needs to happen. So if your program just allocates the memory, if you disable your garbage collector and your program goes on allocating memory, your code doesn't do that. But internally, if there is some metrics going on, you need to log something. Logs are running. So the object for logging. So if that logger object just goes on piling up memory, you're using a third-party library. Your code doesn't do allocations, that's fine. But if you're using a third-party library, that library, if it allocates memory, then the memory would go on piling up because the garbage collection hasn't happened there. So it depends because then you would have to also implement the library and also its dependencies. So it goes on to a spiral. So disabling is always not a best choice.
Any more questions?